So just like we could describe a line using our standard form or scalar equation, but we could also describe a line using a vector equation, the same is true of a plane, except for a plane needs two vectors to describe it. So let's say you've got this plane right here. This plane has two vectors defined by it, so it only has one location it could be. Now imagine that we get rid of one of those vectors. So now we're going to just have a single vector here to try and define this plane with a single vector. Well, that's not going to work so well. I could rotate around that vector, keeping it pointed the same way, and I still have different planes there. I'm not going to have a single unique plane. I still would fit that one vector. But as soon as I get two vectors, well, that's now a fixed plane. I can't rotate it without moving those two vectors. So two vectors is all you need to fully define a plane. So let's see what that looks like in terms of this equation. Looks a lot like your standard form of a line equation, right? It should, because it's very similar to, your vector equation of a line, because it's very similar to your vector equation of a line. This right here is a point on the plane. So point on the plane. Just like in your vector equation of a line, that was a point on the line. So the idea of this vector is take you to the plane. Let's find the plane. Then we have our two vectors that are lying in the plane, parallel to the plane. So this is a vector in the plane. It lies parallel to the plane. And here's another vector in the plane. The only thing we have to worry about with these vectors is make sure they're not parallel to each other. Going back to our single vector picture here, if I had a second vector just like this, well, that doesn't help me define this plane at all. I still could rotate it and not move either vector. I need to make sure my second vector is at least at some angle from the first in order to fix the plane and keep it frozen in space. So these two vectors can't be parallel to each other. So just put that in here. Not parallel to each other. So not parallel to each other, but they both do have to be parallel to the plane or line in the plane. So the idea is that we can get to every point on the plane by first going to the plane, to any point on the plane, and then taking scalar multiples of vectors that lie in the plane. So here's my two vectors defining a plane. I could go starting at maybe this point in the plane. If this is maybe vector A, that's vector B, I could first follow vector A this way. And then maybe I could follow half of negative vector B. That would take me back here. So that's half of vector B, but negative. That takes me to this point here. And I could literally cover every point in this plane by just starting somewhere on the plane at my point, and then using scalar multiples of vectors in the plane, as long as I have two unique non-parallel vectors in the plane. So these right here, these are your scaling constants, t and s. Just like in a line, we had one scaling constant, t, to slide us along the slope. In a plane, we need two scaling constants to slide us along one vector, then over along another. As you can guess, there's parametric equations of a plane too, just like there were parametric equations of a line. So for a plane, our parametric equations for this particular plane would look like this. We'll take the x components first. X here will equal the x component of our point plus t times the x component of my first vector, so 8t, and then plus s times the x component of my second vector, which is just 1, so plus s. Then the y components, same idea. So 7 is the y component of my point, minus 5t here, and minus 3s. And finally, the z components of my plane. There's 0 for the point on the plane, but then we do 4t, and we have a minus 2s there. So those are my parametric equations for this plane. Just like with a line, we can check if there's a point on the line by solving for t and seeing if the t's were the same, if you remember how we did that. We can do the same thing with a plane, but it's a bit trickier because there's two scaling constants here. There's t, but there's also s that we have to worry about. So it takes us a little bit longer, but it's still possible to do. We're going to take our point, plug it in for x, y, and z into our parametric equations of this plane. Then we're going to solve for t and s. But to do that, I need two equations. That's two unknowns, right? So I need two equations. So what I do is I pick any two of the parametric equations, maybe x and y. And then I use those to solve for t and s. Once I've got t and s, I plug it into the third parametric equation and see if I do get out the expected z value. If I do, then that point is on the plane, and if I don't, it's not. So I'll show you what that looks like. So first we write out our parametric equations. X, here's the first one. So x is equal to 1 plus 0t, so I don't have to write anything down there, plus 1s. Then I have y. Y is equal to 3 plus 2t, and then plus 0s. And then I have z. Z is equal to 0 minus t plus 3s. Okay, so to solve for s and t, I'm very fortunate in this case because if you notice my x and y equations just have s or t in them. So the easiest strategy here would be to use x and y. So I'll show us how we could do that. So I'll take x and replace the x with the x component of the point that I'm testing. So 4 for x. And we would solve for s here. What do I get for s? It would be 3. I would do the same with y, so replace y with the y component of the point I'm testing, 3 plus 2t. And here I'm going to get t is equal to, let's subtract the 3, divide through by 2, t would be equal to 2. Then we test out, so we take our s and t that I just found here, and I test them in the third parametric. So what I'll do is I'll make z, hopefully hoping that z equals 7, right, because that's what I want. Z is equal to negative t, so negative 2, plus 3 times s, and s is equal to 3. So that's equal to negative 2 plus 9, that's indeed 7. So that means our point is on the plane. Just to show you how I could do that if it was a little more difficult, let's try starting with parametric equations x and z instead. We could still do it that way as well. So if I have, say, x, the 4 is equal to 1 plus s, and I have the z, the 7, is equal to negative t plus 3s. So here, I actually have to do a little bit of combining equations. I can't start with the z equation right away and be able to solve for s or t. Sometimes you'll get it where there'll be an s and t in every single one of your parametric equations. So you have to combine two in order to figure out s and t. This one is still pretty straightforward though. I can take the s from here, s equaling 3, plug that into here, and solve for t. So I would get 7 minus 9, there 3 times 3 is equal to my negative t, or in other words, t is equal to 2. And get the same thing as before, which is what I'm hoping for. So then I would test these. I'd test in the y equation. Y is equal to 3 plus 2t. In this case, I only have to pull in the 2, so y would equal 3 plus 2 times 2, which is indeed 7. Shows us that indeed this point is on the plane. So this is a point that physically lies in the plane. It's attached to the plane. It's not sort of floating above the plane. That's what we just found out. Right, planes have x and y intercepts, right? So if you imagine a plane here, get out my plane is going to cross an x-axis at some point. It'll sort of stab through the x-axis. Sometimes it might go parallel to the x-axis, in which case it won't necessarily cross, but most planes are going to have an x-intercept, a y-intercept, a z-intercept. So how do we find that? Well, our strategy is very much like finding the x-intercept of a line. For the x-intercept of a line, we'd set y equal to 0 and z equal to 0. The same is true of a plane, right? When you cross the x-axis, draw us a little picture here. Here's z, here's y, here's x. if you're crossing the x-axis with your plane right here, at that moment, z is equal to 0. You can see you're at a height of 0. And also y is equal to 0 as well. You can see that we're at 0 for y. So that's our strategy for finding any kind of an intercept of a line or a plane. We set y equal to 0 and z equal to 0. So let's write out our equations, our parametric equations here. I have x, that's the one I don't know. X is equal to 1 plus t times 1, so t, plus s times 1, which is s. And then I have y. Y is equal to negative 2 plus 0t, so nothing there, and then plus a single s. And finally, I've got z. Z is equal to negative 2 as well, plus 4t plus 3s. So what I need to do is set both the the z and the y equal to 0 in order to find that x-intercept. So I'm going to set both y and z equal to 0. Now, just like before, sometimes this will happen where one of these has both an s and a t, or maybe both has both an s and a t. If both y and z have an s and a t, I need to combine two equations, two unknowns, to figure out both s and t. In this case, I'm really lucky. Y just has an s, so